Shaila ma'am, start your recording.
Yes, ma'am.
Sampada ma'am, please share your screen.
Yes, ma'am.
Sir, shall we start?
Yes. Am I audible?
Uh,
Very
yes,
much.
sir. Sampada ma'am, please start.
Yes, yes. A very warm and pleasant evening to one and all present here. We welcome you all to our seventh session of 6 days online ATAL FDP, that is Introduction to Quantum Computing Concepts and Capabilities. I, Professor Sampada Lokhande, on behalf of the Information Technology Department at AC Patil College of Engineering, Kharghar, welcomes Mr. Shashank Sarma sir to the ATAL FDP on Next Generations Computing, Advances in HPC and Quantum Technologies for Data-Driven Insight. Without further ado, allow me to introduce Mr. Shashank Sarma sir, Scientist D at CDAC, where he leads AI application development and benchmarking in HPC technologies. With an MTech from IIT Kharagpur and over a decade of experience in AI, computer vision, and HPC, he has contributed to the National Supercomputing Mission. Mr. Shashank sir has developed advanced face recognition solutions for security agencies and is certified by NVIDIA and Intel in accelerated computing and SYCL. He is currently advancing projects in quantum computing on HPC platform. We welcome you, sir. Please accept our virtual token of respect. Now I request Mr. Shashank Sarma, sir, to start the session. Over to you, sir.
Yes. Thank you, ma'am. I'll just share my screen. So I'm
Yes,
joined
sir.
from two devices.
Stop the
So I will be
presentation.
sharing my screen from the other device. Just I think the screen is visible.
Yes, sir.
Yes, sir.
Okay. So thank you, ma'am, for the introduction and for inviting me to speak in this very peculiar topic of quantum computing in general. So the session is basically introduction to quantum computing. I'll be talking about some of the underlying concepts of quantum computing, and we'll be discussing about operational cycle of quantum computer as well. So to start with, these are some of the quotes from famous personalities in this field. Starting from Richard Feynman, it's one of the pioneering physicists who worked on this field. So what he said, I think 5-6 decades ago, was that he was working on quantum mechanics, and through quantum mechanics, people realized that nature isn't classical. So the particles that you see, electrons, protons, and all those things, does not behave in a very classical way. So in order to explain the experimentation, people come up with quantum mechanical theory. And he basically suggested this idea that if you want to simulate the laws of nature, which are now quantum mechanical, you better use quantum mechanics in your computational devices as well. So that was sort of a start of the idea of quantum computing in general. Now it has become a very buzzword. So there is another quote from Michio Kaku, who is another physicist, and it's basically he's telling us that through quantum computing we can solve some problems which we once thought were unsolvable, like the problem in quantum chemistry. Right? So anything that is related to simulating nature, which is driven by quantum mechanical laws, uh, if we are trying to simulate it using classical computers, we are just approximating the things. So in order to get the accurate solutions, we have to move towards quantum computers. And that's why he is saying that we can solve problems which we thought once were unsolvable. Right? And the third quote is actually sort of a question for me. So it's a quote from Chris Bernard. He's saying that verbal description often give you the impression that we have understood something when we really haven't. So the thing is, whatever I'm going to talk about today, it might give you an impression that I know certain aspects of quantum computing, but still I'm a student in this particular area and I'm still learning. So this presentation actually is going to work both ways. I'll be introducing some topics to you. In turn, I'll get uh, where are the gap areas in my understanding as well. So feel free to ask as many questions as you want. Right. So also, so if there is any gap, since we are doing this online, so there might be gap in slide transitions and all those things. There could be some audio problem or some technical problems. In that scenario, please feel free to mute yourself and let me know. So if I'm going out of sync, I'm going fast, you're not able to hear me or follow me, please stop. Okay. So to begin with, let's try understand the what and why of quantum computing. What is quantum computing? As I told earlier, by Feynman, he said that in order to simulate nature, we might require quantum computers or that sort of programmers. So why that is the case? Because in computation, we try to simulate physical phenomena and we are bounded by the formalism behind it. And what is the formalism of classical computer? It's actually Boolean algebra. And Boolean algebra is deterministic. But quantum mechanics tells us that nature is not deterministic, it's probabilistic. That's why quantum computer is basically introducing a new paradigm, with which we can utilize the underlying formalism of quantum mechanics, and we can utilize those formalisms to simulate nature better and accurately, right? And why? So why you should invest your time, or I should invest my time in this particular area is there are already several prospect areas. So two of them which are very known or useful algorithms are given by Shores and Grovers. So whatever we are doing right now in internet and computing world, it's driven by the encryptions, right? The RSA encryption. So RSA encryption, the underlying mathematical structure is that it is based on factorization of large composite numbers. So what it says is basically you cannot factorize a very large composite number into two prime factors, or you can do it, but it's going to take a lot of time. Right? So Shores basically presented an idea using quantum computers. You can do it in minutes or in seconds, depending upon the size and the technology of quantum computer that you have. So it's sort of a theoretical algorithm that he has devised to show that there is a utility of quantum computer in other areas as well. Right? And another such algorithm is Grover's algorithm. So you think about a big list, right? And it's an unordered list. So for classical computer to search anything in that unordered list, it will require order and time complexity, right? And is the size of your input space. But Grover's actually gave an algorithm which can do this particular job in root n, Right? So this might not be a big difference, but if you say the input size is the whole internet, everything that is there in web and you want, and it's anyways in an unstructured format, if you want to search anything, so it will take a lot of time. But using Rovers, you can reduce the time by square root, and that is a big impact. It is also believed that is going to give speed up in various quantum chemistry application, drug discovery, and all those things. But that is yet to be proven. So all of this are theoretical algorithm as of now. But because of this theoretical algorithms and the mathematics and everything behind it, people in many industries, from automation to pharmacy to communication, everywhere, people are now making themselves quantum ready. Right? So this is another reason you should join this particular area. Then there's, because of multiple industries getting involved, there is a growing demand of professionals who are skilled from the top layer to the bottom layers, from vision decision makers to the lower level implementers. So every facet of the things people are required, skilled labor is required in this particular area. And the last point is very interesting. That is why I joined. And because it combines various domains, it combines computer science, physics, mathematics, engineering, and it is sort of in a conjunction of all this particular domains, and it's very exciting, intellectually challenging. And once I started learning quantum mechanics, it's actually outside, completely outside your intuition of how you perceive reality in general. So all of these things makes you learn quantum computing, right? Now, what is the objective of this particular session? So I have kept two things in mind. So I've divided it roughly in two sections. In the first section, I'll be talking about quantum computing concepts. So the idea or the picture that I have in mind is that I'll give you some tools. I'll introduce some tools and technology so that you can understand quantum computing from a computer scientist perspective. So I'm assuming that most of you all are from computer scientist background, or those who are from other backgrounds as well, know computers or computing in general. So I'll be starting with them. So I'll be introducing all the basic tools that you would require in order to understand anything in future. Right? So that is the purpose of introductory session anyways. And the second is, I wanted you to get a glimpse of the operational cycle of a quantum computer. Right? So from programming to hardware execution to getting the result out, what is the whole cycle that you have to go through? Now, delving straight into classical versus quantum. Actually, this particular thing is a misnomer, classical versus quantum. So when we see the quantum system organization, you get to know that it's not essentially quantum versus classical, but this is the buzzword that is going on right now. So what is that? So in classical computer, we all already know that the fundamental entity that we deal with is bits, and bits can take two values. It's either 0 or it's 1. And how do we manipulate bits? We manipulate bits using gates. So you have your AND gate, OR gate, NOT gate, and all those things. So these are basically Boolean logical operators. And then we have our algorithms. So you have a real problem. You divide that into a sequence of steps. And this sequence of steps you program, which essentially boils down into this smaller gate operations at the very computer architecture level. So that is the essence of classical computing. And the whole thing is governed by Boolean algebra. As such. Now coming to quantum computing, the fundamental unit here is an abstract unit called qubits. Now qubits, the states are probabilistic and are represented by vectors. We'll look into this two aspects in a great detail in the coming slides. But for now, just keep that in your mind, that qubits are states which are probabilistic and represented by vectors. So if I say 0, so 0 in quantum computer will be represented by something like this. It's a vector of size 2. So it contains two values, 1 and 0, and 1 is represented by two values, 0 and 1. Similarly, in quantum also, we have gates, logical gates, which are basically represented by matrices. Why matrices? Because our qubits are vectors. So we'll see how this all plays into. And then we have something called quantum algorithms, which are a sequence of gate operation on qubits. So again, we are manipulating. So in classical computer, we are manipulating bits. In quantum computer, we'll be manipulating qubits. And for that, we'll be requiring gate operations, right? So it's a sequence of gate operations. And the whole thing, since we are dealing with vectors and matrices and all those things, is actually governed by linear algebra. Now let's basically start with qubit representation. So throughout this presentation, whatever concept that I'm going to talk about, I'll be giving you a linear algebra revision of that, because that is the underlying structure of everything. So I told you that qubit is a vector. So in order to learn qubit representation, we'll be looking into vectors as well. So what is a vector? So in mathematics, it's just an object that has magnitude as well as a direction. Right? So it's a mathematical object with magnitude and direction. So it's represented by this sort of a vector. This is a column vector, right? So it's a 2 cross 1 column vector with ax and ay as two values. We can calculate the magnitude and direction of this. So magnitude is basically the x component and y component is squared and is square root of that. And your direction is basically represented by this theta, ay and ax. So you can see the visual representation here. If this is my a, then ax is my magnitude in this direction, ay is my magnitude in that direction, and this theta is the actual direction. Okay. So this is what a vector is. The next point of linear algebra that you should know before moving forward is the basis vectors and projections. So what are basis vectors? So basis vector are basically a unit vector in particular direction. So let's say I have two direction x and y. So basis vector are a unit dimensional vectors in this direction x, and this will be my y unit vector. And why this is important? Because from this representation, I can go to a representation which is a representation of superposition. So what I can say with this representation is that you move ax in this direction, x direction, you move ay in this direction, and you'll get to this direction. So another representation of this column vector is this superposition representation. Okay. Then we have a dot product of two vector, which is if I'm doing, this is again an operation. If I'm doing dot product, this is my output. It's magnitude of A, magnitude of B, and cos theta, where theta is the angle between A and B. Okay. And what are projection? Projection is basically if I throw a light from this point, what is the value in this direction, right? So if you want to calculate, you can use dot product for calculating the projections as well. So these are the very basic linear algebraic representation you would require for the coming section. Now coming back to qubit representation. So for representing qubit, we use something called Ket notation. So it's proposed by Dirac, which is again a physicist. It's named after him. So it's basically a line and this. So this is my Ket notation. So anything I write in between is my vector, state vector. Okay. So I've shown you in the earlier slide that it was the 0 vector was represented by this and 1 vector was represented by this. It's 1 0 and 0 1. Okay. But since these are vectors, what is the value that this and this can take? There is not just zeros and ones. We can have any values. So an arbitrary state is defined by size A and B, where A and B can take any value in complex plane, right? So A and B are basically two complex numbers, and it can take any value given this constraint. What is this constraint? the magnitude of the first value squared plus magnitude of second value squared is 1. Okay. So that is the constraint that we have. So it cannot just take any values. It has to take those values from this particular constraint. But then again, in Boolean algebra or in bits, we saw that there are only two possible values, 0 and 1. But here, even though we have this constraint, we have infinite number of possibilities. So my state can be anything, right? So the number of state that I can deal with is infinite. Now comes to superposition. So since we can represent vector in the superposition form, we can represent qubits in superposition form as well. So if I take this two vectors, which are again will come again and again to this, come back to this two vectors, because these are called as basis vectors in one direction and another direction. Okay. So if I consider 0 as one basis vector, 1 as one basis vector, then I can write any arbitrary state A and B in superposition form. Right? How I can write it? So I can write it, I can go A multiplied by this, B multiplied by this. Okay. So it can be represented as A 0. So A in this direction plus I'm going B in this direction. So that is the superposition representation that we have. So in this scenario, this 0 and 1, what I call is basis vectors or basis states. Okay. And A and B are bounded, but scalar values. Right. So this is another notation or representation of a qubit. I'm just talking about the representation as of now. The implication, the consequences, we'll see later. Now let's see a geometric representation. I've already shown you. If in the x direction I'm considering this 1 and in y direction I'm considering this 0. Actually, I've misplaced this. In this direction it should be 0, in this direction it should be 1. Then my state here it will be A, here it will be B. Okay. So this is again a geometric representation of the same thing that we have seen. Okay. There is a typo there. This should be 1 and this should be 0. Okay. Now let's go to multi-qubit representation. So you know that multi-bit representation, since it can take only zeros and 1, I can represent it as a string. So I can take a string, I can represent 1 0 0 1 1 or something like that, right? So these are my multi-bit representation. But since qubit are vectors, I cannot represent them in this string format, right? I need to use some sort of mathematical structure for that. Let's see what that structure is going to be. So again, coming back to linear algebra, here we'll be using tensor products, right? So tensor product, just take this as a formula of tensor product. So you have two vectors A and you have a vector P, and these vectors are basically 2 cross 1, 2 cross 1 vectors. The values are A, B, and P, Q. So what you will do, you will take this, multiply with this vector, you get the first two values. And then you take B, multiply by P and Q, and you get last two values. And my resultant here is going to be 4 cross 1. Right? So it's basically mapping of two two-dimensional vectors in a four-dimensional space. So this two vectors were independent in their two-dimensional space. I'm mapping this two in a four-dimensional space. So I'm blowing up the dimension of these two vectors in this representation. Okay. So in general, this is applicable for any two vectors. So let's say I have a m cross 1 vector and I have a n cross 1 vector. I can do a tensor product and I'll get a mn cross 1 vector. So it's blowing up the dimension. And that is what tensor product operation do in linear algebra. The same thing we'll do for our multi-qubit representation. Okay, we'll be using tensor products. So I'll take two states, state psi1 and psi2, and I'm going to represent it as a single state, psi1, psi2. Now, this is a 2D space, this is a 2D space, complex space, but this is going to live in a 4D space. Okay, that is the whole idea of it. So if my values of this vector was a1, b1, and value of this vector was a2, b2, then what I'll get? I'll get this four values: a1, a2, a1, b2, a2, a1, and a2, b2. Right? Now let's see with an example how I can represent this particular thing. So let's say I have 0 and 0. I want to do a tensor product of that. Then it's basically 1, 0 and 1, 0. So 1 multiplied by 1, 0 will give you 1, 0, 0, 0. And 0 multiplied by 1, 0 will give you this. Right? So you'll get the representation of 0, 0 as this vector, 1, 0, 0, 0. Similarly, representation of 0, 1 is this vector, 0, 1, 0, 0. 1, 0 is 0, 0, 1, 0. And 1, 1 is 0, 0, 0, 1. Now, these are four very peculiar vectors in their sense, in that sense, okay? So, again, going back to superposition, I can represent psi1, psi2 as superposition of four vectors, which is my 0, 0 plus b 0, 1 plus c 1, 0 plus d 1, 1. So in this scenario, 0, 0, 0, 1, 1, 0, and 1, 1 are my basis vectors for two qubit representation. Okay. The consequence of this kind of representation is that if you want to represent, let's say, n qubits, then the vector length blows up to 2 raised to power n because we are using tensor products, and that is the representation that we have as of. Okay. So this is how we can represent multiple qubits as well. So single qubit is a two-dimensional vector. Multiple qubits, let's say if it's k qubits, then the dimension would be 2 raised to power k. But again, that would be a vector only. So this was vector, this is also a vector. Okay. Now the second piece of puzzle, that is qubit operations. So now we have seen how qubits are represented. In the next couple of slides, we are going to see what are the operations we can do on those qubits. And I told you in the first slide, the operations are going to be matrices. So let's revise this matrix, matrix vector multiplication, which is basically this formulation. So for a 4 cross 1 vector, in order to transform this 4 cross 1 vector, you would require a 4 cross 4 matrix, right? And matrix multiplication goes like this. You take this row, take this column, and you will get this row. Okay. In the similar fashion, I'm going to multiply everything and I'll get a 4 cross 1 vector as a resultant vector. Okay. So it's basically multiplication and then summation. Okay. And what essentially it's doing, it's taking a vector from this to this. So this is basically a transformation. Okay. So A is getting transformed to B. And what is the transformation matrix? This one. So here T is my transformation matrix, which is transforming A from one direction to another direction. It might be rotation, it might be scaling up, it might be something else. Okay, but it's essentially transformation. So the thing about this is, since it's a transformation, this is always going to be a square matrix, right? So that the dimensionality of the resultant remains the same. So we know if I increase this dimension, let's say I'm taking a 5 cross 4 transformation matrix and applying it on 4 cross 1 vector, then what would be my dimension? My resultant dimension would be 5 cross. But I want to stay in that same dimension. That's why this has to be a 4 cross 4 matrix, which is a square matrix. Okay. Coming to Operations, again, we'll start with classical operations. So on a single bit, what sort of classical operation you can do? So there are 4 fundamental operations that you can perform on a bit, which is identity, negation, constant 0, and constant 1. So identity is basically you map input to output, you're changing nothing. So it's a linear one-to-one mapping. Negation, you are doing this sort of a cross mapping. Then in constant 0, both the inputs are getting mapped to 0. And in constant 1, both the inputs are getting mapped to 1. So if you pass either 0 or 1, it will go to 1. Something like that. Okay. Now let's see the quantum equivalent of these 4 operations. So I told you the quantum operations are going to be represented by a matrix. So we'll see how we can reduce this to get notations, first of all qubits, and then how we can transform this matrix to that this vector to that vector using matrices. That is the whole exercise. Okay. So again, the identity, I have replaced everything by get notation. So it's not a 0 or 1, it's 0 and 1. Okay. And here for identity, 1 0 goes to 1 0, 0 1 goes to 0 1. For negation, 1 0 goes to 0 1 and 0 1 goes to 1 0. For constant 0, whatever the input is, it will go to 1 0. And for constant 1, whatever the input is, it will go to 0 1. Right? So let's see what are the matrices. So essentially, in order to transform, I'll have some transformation matrices. So T, I, Tn, Tc0, and Tc1, let's say, are my transformation matrices. Then what are going to be the value of this transformation matrices? Is this. So this is my Ti identity matrix. The flip of this identity matrix is my negation matrix. So if you perform this operation 0 1 and 1 0 to this 1 0, it will go to 0 1. Right? So it's basically flipping the two values. Then constant 1 is this matrix with both the first row as 1 and both the values on second row as 0. And the reverse of that is constant 1. In row 0 it's 0 and in row 1 it's 1. Okay, so these are basically matrices that I can define for this particular 4 operations, fundamental operations on a qubit. Okay, but there is a constraint in this as well. What is the constraint? That qubit operations has to be reversible. Now, whatever constraint and whatever representation I'm talking about is coming from quantum mechanical postulates, right? And I will not be talking about quantum mechanical postulates because this is a very introductory session. It will confuse you. So we'll be talking about the computer science perspective, right? So there is a restriction on reversible operations. So what is a reversible operation? Let's say I give you an input and a function. So let's say I'm going to give you, output and a function. So let's take this operation. Okay, identity is an operation. I'm going to give you the output. Let's say my output is 0. Since this is identity and I know the output is 0, I automatically know the input is 0. Similarly goes for negation. Let's say I'm going to say the output is 0 and operation that I've performed is negation. Then I can revert it back to the input. I can calculate the input. The input is going to be 1 because negation is a flip operation. But the last two operation, this is not possible. Suppose I give you my output is again 0. I cannot guess what my input is going to be. It can be 0, it can be 1. Right? So this particular mapping is a irreversible operation. And this mappings are basically reversible because there is a one-to-one mapping between input and output. And in quantum computing, each matrix that you will see or each operation that you are going to see are essentially going to be a reversible operation. Okay. In another word, if this is my Ti, then I can calculate the inverse of this matrix as well. That is the whole thing. Okay. In addition to this, we have seen that A and B, if my state is defined by A and B can take any arbitrary value as well. So it's not just about zeros and ones. So apart from those four fundamental operations, you have one very generic operation called rotation, right? So it's basically transforming this state into any other state. Okay, so you can do this via rotation as well. So rotation is another operation that you can have as a transformation operation in qubits, right? And these are basically rotation matrices. Now you might not be able to understand this because till now we have only seen A and B as real values. So if A and B are real values, this is basically a rotation matrix. But since A and B are complex, we have a representation like this where I comes into the picture. So there are three different directions in which you can rotate, basically. Now that we have seen qubit operations, let's go to measurement. So I've told you that a psi is represented by two complex numbers in a vector form. But I haven't told you what essentially is the meaning behind these two values, right? They are complex values, but what is the meaning? What is the physical significance of these two values? Actually, these complex values are known as probability amplitudes. So A and B are probability amplitudes, right? So in first slide, I told you my qubits are first of all vectors, and there is some sense of probability in it, right? So this A and B value basically brings in probability as well. How? So going back to my superposition form, A will give me some sort of indication of the qubit value going to 1, 0, and B is going to give me some indication of qubit value going to 1, right? And this we can define in terms of probabilities. So probability of psi going to 0 is represented by this particular expression, which is amplitude of A square. And probability of psi going to 1 will be represented by this, which is mod of B square. Okay. Now you can go back and understand this constraint. This constraint is very clear. So it's either probability of going to 0 or probability of going to 1. So if we sum the probabilities, my output should always be 1, right? Because the sum of probabilities is 1. That is where this particular expression comes from, that particular constraint. Okay. Let's look at it in more detail. When I say psi going to 0, what does this mean? This means is that psi, the state is not observable at all. The actual state of system is not observable. So when I perform an experiment, the output is always going to be this basis states. So output always get 0 or 1, no matter what. But there is a probability behind it. Right? What that means is, if my psi is A and B, then the state collapsing to 0 is with probability this and 1 with probability B square. Let's devise an experiment for this particular thing. Let's say I have my input state as 0 and I have a black box operation, which is moving my psi to 1 by 2 root 3 by 2. Okay, this is the transformation that this is happening. Now, if I measure this particular thing and I run this experiment 1,000 times, then what will happen? Approximately 750 times I'll get 1, and approximately 250 times I'll get 0. Why? Because probability of 0 here is going to be 1 by 2 square, and probability of 1 is going to be root 3 by 2 square, right? So if I run this experiment one time, I might get 0 or 1. But if I continue running this experiment 1,000 times, 10,000 times, it will essentially converge to this probabilities. And that is where the state comes into play. So that is one of the reason. And the second thing is, I'm saying that it collapses to 0 or 1 means now the state that I'm observing is basically 0. Okay, so there is no ambiguity as such whenever we are observing. So whenever we are observing, we'll get either 0 or 1. There is no ambiguous nature of this. Okay. But the actual state could be anything between 0 and 1. So that is the measurement hypothesis that we have in quantum mechanics that extends to qubits as well. And this unique properties give quantum computers the power that it has. So we have seen some gate operations, but there are some very standard gates. So we'll look into single qubit gates. So we have, I'm going to introduce two very specific and very useful gates, which are Hadamard gate and Poly-X gate. Okay. Hadamard gate, again, gate are represented by matrix. In this case, it's going to be a square matrix of size 2 cross 2. Okay. What is the purpose of this Hadamard gate? Its values are 1 by root 2, 1 by root 2, 1 by root 2, and minus 1 by root 2. And let's say I apply this particular gate to a qubit, which is 0. What I'll get? I'll get 1 by 2, 1 by 2. Right? So this puts any basis state 0 or 1 in equal superposition state. Equal superposition of 0 and 1. Why that is equal? Because it's 1 by root 2, 1 by root 2. And if I square this, I'll get 1 by 2, 1 by 2. That's why these are equal superposition states. Right? And that is the significance of a Hadamard gate. The next is X gate. We have already seen X gate is nothing but a negation gate. If I apply it to 0, it will be 1. If I apply it to 0, it will be 1. And if I apply it to 1, it is going to be 0. So x1 will give me 0. Yeah. But what if I'm dealing with any arbitrary state? Let's say if I apply x to a psi, which is, my psi is a b. So what it will do, it will flip the probabilities. So earlier the probability of collapsing to 0 was correlated to a, but now it is correlating to b. So in case of my standard basis state, it acts as a negation. But when I apply it to any arbitrary qubit, it will flip the probabilities of 0 and 1 basis state, basically. Okay, and that is the significance of Poly-X gate. This is again a very useful state machine representation of quantum gates, right? So I have taken very specific states. So this is my 0 1, this is my 1 0, this is my again 0 minus 1, minus 1 0. And when I move, how I will move if I apply a Hadamard gate. So let's say if I am in this state, if I apply Hadamard, it will go to this state. If I am in this state, I apply Hadamard, I'll go back to this state. Right? 1 will go to this, minus 1, 0 minus 1 will go to this, and minus 1 0 will go to this. So these are interchangeable state. We'll see how this unit state machine will work out. Okay. Similarly, we have the same thing for X. Right? This is for Hadamard gate, this particular representation. This is for X gate. So my X gate, if the value is 1 by root 2, 1 by root 2. If it is a equal superposition state, then even by flipping the probabilities, I'll come again back to this, right? Similarly with minus 1 by root 2 minus 1 by 2, even if I flip this, I'll come back to this particular point itself. Rest of the points are, we are just flipping back and forth. Okay. Now let's say how a quantum algorithm works. Okay. So I told you quantum algorithm is a sequence of operation. So I'll be applying a sequence of gate in order to transform a particular qubit to another qubit. And that is the essence of it. So let's say this is my algorithm that I have defined. This algorithm is interchangeably used with circuit also. Okay. I see there are some questions, so I'll stop here and I'll just try to answer some of this. Somebody has raised their hands. Can you unmute yourself if you want to convey something?
Sir, there are two questions in the chat box.
Yes. Uh,
Some ask, is it necessary to use Keras only in TF, TensorFlow?
that is basically related to AI. So here we don't use Keras or TensorFlow as libraries. Here we are going to use Qiskit, let's say. Or there are some other libraries from Circ and all those things which you can use for this sort of circuit manipulation. So basically, you can draw this sort of circuit in a framework like Qiskit, which is very easy to use. Again, it's a Python library, so you can install it using PyPy. So pip install you can do, and you can start designing your circuit. So if time permits, I'll squeeze in a demo of that as well. Okay.
One more question is there. Is it possible to use qubit rotation in scheduling problem?
Okay, scheduling problem. Can you just explain a bit what is the scheduling problem that you are talking about?
Ankush sir, Ankush Patil sir, can you please unmute and ask your question more precisely?
Okay, sir, we will take that
Yeah.
question afterwards.
Yes. Since this question has come up, I'll just tell you a bit about this. So let's say if you want to map any real problem like scheduling problem, if you want to solve it using quantum computers, then what it entails. So maybe I'll talk about this when I'll show you that the whole operation cycle of quantum computer. Then we can talk about this particular problem as well. Okay. Now let's focus on this quantum algorithm, which is again a sequence of gate operations. So it's X, H, X, H, X, H. So you can go around the unit circle. I've started with 1, 0. I'll go to the 0, 1. I'm applying X. Then I'll come back to 1 by root 2 minus 1 by root 2. I'll again go back to this negative 1 by root 2, 1 by 2. Then using Hadamard, I'll come back to this state. And using X, I'll come back to this state. And that is going to be my output. So this is just like a state transition machines. I can draw this for a very specific states like this. These are all special states. All of these are special states. But any arbitrary state you can calculate using my matrices. Okay. So up until now, what we have seen two gates, which is Hadamard and which is X gate, and both are single qubit gates. We have another very special gate called C0 gate, which is a 2 qubit gate. It operates on a pair of qubits. Okay. So what it is, let's say I have a control bit and I have a target bit. So what it essentially says is, if my control is 0, I'll keep my target as is. But if my control is 1, I'll flip my target. Okay. So let's say this was my control bit and this was my target bit. So if control bit is 0, I'm not going to touch. So 0 is going to 0, 1 is going to 1. And if my control bit is 1, I'm going to flip. Okay. And if in the matrix form, since it's a two qubit gate, the dimension of it is going to be 4 cross 4. And it's essentially an identity matrix with the last two row reversed. Okay. This is again a very important gate to know. Right. Now I've just shown how this particular thing works using this operation. So you can apply this matrix on 0 0 matrix, sorry, 0 0 vector, and you'll get your result. Okay. So you can look at it at this operation end to end. Right. So this is how you can operate. So here, note, by applying this, I'm doing this on 4 cross 4, 4 cross 1 vector. I am getting a result in 4 cross 1, 4 cross 1 vector, and I am factoring it basically into 2 qubits. Okay. So here I was blowing up. Here I am reducing down the dimension. I am basically factoring. I am trying to find out what is the value of each individual qubit. Okay. Well, let's see how the behavior is when I go to arbitrary states. So when I go to arbitrary states, again, what this will do is this will flip this 2. This operation is going to flip this 2. So my output now is going to be A1, A2, A1, B2, here A2, B2, and A2, A1. Now let's see whether I can factorize this or not. So these are very generic state representation, right? So let's try and factorize this. So I'll factor out A1, I'll factor out A2. What will be my remaining thing? A2, B2. But at the bottom side, you'll get B2, A2. Right? And this is the problematic thing. So you cannot factorize any general state. It was easier to factorize when these were basis states, 0, 0, 0, 1, 1, 0, 1, 1. But any arbitrary state, you cannot factorize it in this format. Right? And that is the basically source of quantum entanglement. So once you apply a Q node, C node gate, it will create it in certain scenarios, it can create quantum entanglement wherein you will not be able to factorize it anymore. And that is the mathematical description of quantum entanglement. Okay. So to define it properly, if a product state of 2 qubits cannot be factored, then they are said to be entangled. Okay. What this means is if I want to factor this state into these two states, I have to have solution of this equation, which is x1, x3 should be equal to A, x1, x4 should be equal to B, x2, x3 should be equal to C, and x2, x4 should be equal to D. So if I find the solution of these 4 equations, then only I'll be able to factorize. Right? So in this scenario, let's say if my input was 0, 0, 1, 0. Let's see whether I can factor it. So my x1, x3 was 0, x1, x4 was 0, x2, x3 was 1, and x2, x4 was 0. So I could find one set of solution for which this particular set of equation works. And which is this? My x1 is 0, x2 is 1, x3 is 1, x4 is 0. So I can break it down. But let's see a scenario in which this does not work. Okay, which is this scenario where x1, x3 is 1 by root 2, x1, x4 is 0, x2, x3 is 0, and x2, x4 is 0. So let's start with this. x1, x4 is 0. That means either x1 is 0 or x4 is 0. Let's say if x1 was 0, then this expression should have been 0. Let's say if x4 was 0, then this expression should have been 0. So we have no solution to this equation. That's why this particular state cannot be factored. And this is a quantum entangled state. This is a very peculiar state which is called also known as a Bell state. What is the consequence of a Bell state? So this is my Bell state. Psi 2 represents that it's a 2-qubit state. It's not a single qubit state. Okay. And if I draw in this superposition format, that means the state getting collapsed to 0, 0, the probability is 1 by root 2 square, which is half. It collapsing to 1, 1 is also half. What this essentially means is, let's say I have produced this state somehow, okay, and I'm measuring 1 qubit. I'm measuring, let's say, this qubit. And if I get 0, then there is no need to measure another qubit, because I know that other qubit state is always going to be 0. And if I measure 1 qubit and its value is 1, then I know the value of other qubit is going to be 1. So I don't have to measure two states separately. Or measurement of one state is affecting the measurement of another state. And that is the consequence of quantum entanglement. And this is very fascinating thing, that this works regardless of any physical conditions, right? So to give you an example, it was a very famous EPR paradox example. So what was it? Let's say you entangle two qubits, and these qubits are physical entities. And let's say I have one qubit and you take another qubit to, let's say, China or USA. Okay. Regardless of what the distance is, if I measure my qubit at 0, the other qubit automatically collapses to 0. Right? So there is this constraint. Space is not a constraint when it comes to entanglement. Only you can send an entangled bit qubit to another planet if you want, and you'll get the same results. And that is the underlying one of the postulates of quantum mechanics as well. Now, how we can create entanglement? I have shown you that we can create entanglement using C0 gate. So let's say I have a very standard basis state 0, 0. If I want to entangle this state, I'll just introduce a Hadamard gate in between, and then a C0 gate. This basically is the representation of a C0 gate. Okay. What this will do, this will change the probabilities. It will flip the last two rows, and my final result would be again a Bell state. Okay. So this is putting one of the qubit in equal superposition. Then I'm doing a tensor product. Then I am doing a flip operation, because it was C0. C0 last two rows, you flip the amplitudes. Okay. So this is how you can generate an entanglement. So this is basically a very famous entanglement circuit, right? So let's summarize whatever we have learned. So first section we saw qubit representation, which are vectors and superposition of basis states, right? The second thing is what were the values? Values were complex numbers, and state vectors are normalized, which means a square plus b square is essentially equal to 1. How we are representing multi-qubits? We are representing multi-qubits using tensor products. And the length of vector is 2 raised to power n, when n is the number of qubits. Okay. What are qubit operations? They are matrix vector multiplications. Right? So my operators are known as gates, and gates are essentially matrices. We have seen three special gates: Hadamard gate, X gate, and C0 gate. These two are single qubit gate. This is a two qubit gate. Again, what are algorithms? Algorithms are sequence of gate operations, one after another. Okay. Measurement collapses the state of a system based on probability, and the amplitudes are given by the values of contained in those vectors. And the second major thing is that any arbitrary state A and B is not observable. Only basis states are observable. I can only observe basis state if I do a measurement. I will not get A, B, or anything else. Right? Lastly, entanglement. So in entanglement, the essence is that multiple qubits, when they are grouped together, and if you perform certain set of operations, they loses their individuality and they start affecting each other. So if I measure one qubit, it will affect the measurement result of another qubit as well. And the mathematical formulation is that it cannot be broken into product form. So I can give you any arbitrary state. If you're not able to break it into two separate states, that means they are entangled. Okay. Now let's see an example. So here I'm going to present an example of Deutsch oracle. The problem is simple. So let's go back to problem description. What is the problem premise of Deutsch oracle? We have seen 4 basic operations on single qubit: identity, negation, constant 0, and constant 1. Right? Now imagine you have a black box implementation of this 4 implementation. So I have a black box which contains either identity, negation, constant 0, or constant 1 function. Okay. And I can only probe this black box. I can give some input, I can observe some output. So I don't know what is inside a black box. Then the question is, so I get identity and negation, I'm going to call it as a variable function. And constant 0 and constant R, we are going to call it as constant functions. Okay. So identity, negation, variable, constant 0, constant 1 are constant functions. And my premise is I have to find out whether the implementation given to me is a constant function or a variable function based on just providing inputs and observing outputs. And let's say how many queries it will require on a classical system and how many queries it will require on a quantum system. Right? And that is the whole idea of it. In the beginning, I told you in some problems, quantum computing is going to give you a speed up. And this is one such dummy problem which shows the capabilities of quantum computing. Okay. Now let's see the classical implementation of black box. If it's identity, X is passing through and through, nothing is there. If it's negation, we are putting a NOT gate in between. If it is constant 0, it's basically don't care, and you are connecting ground to the output. And if it is constant 1, again, input does not matter, you are applying source to your output. Okay, these are 4 implementation. Now let's see how many queries it would require in a classical system. Okay, let's say I have given query 1 as 0 and I am getting 1 as output. If I'm getting if my input is 0 and I'm getting 1 as my output, I can infer that this function, this black box function, is either negation or constant 1. Right? Similarly, if I'm getting 0, I can say that it's an identity or a constant function. Okay. So using just a single query, I cannot discern whether this the black box is constant or it's variable. I would require another query, which is query 2. In query 2, I'll input 1. And if I get 1, that means it is a constant 1 function. Because with 0 also I was getting 1. With 1 also I'm getting 1. That's why it's a constant function. If I'm getting 0, that means it's a negation. With 0, I was getting 1. With 1, I was getting 0. Similar is the case for the bottom half as well. So I'm inputting 1, I'm getting 1. And if my first query was 0, then it's an identity. If my first query was 0 and the second query output is 0, it's constant 0. So how many queries it requires for a classical system to solve this problem? 2 queries. Now let's see how we can solve it using quantum system. Okay, I told you that quantum system cannot implement non-reversible functions, but that is not entirely true. They can implement, but they cannot directly implement. All we need are auxiliary qubits. Okay, so with auxiliary qubits means extra set of qubits. Auxiliary means extra. And C0 operation, we can implement non-reversible functions as well, but you would require to increase the number of qubit in that sense. Okay. Now let's see how I can implement a constant functions using quantums. Okay. So constant 0, this is my control qubit, this is my target qubit, and output I'm measuring here. Okay. And target, I'm always keeping it as 0. Right? I'm providing input through this port, I'm calculating output through this port. Okay. So the internal connection are just plain and simple. Right? So for constant 0, since my target was already 0, I'm measuring 0 in any case. So X is basically a don't care in this. And if it is constant 1, again X is a don't care because there is no interrelation between these two inside. And I'm just applying an X gate. So 0 will become 1. And that's how I can implement constant functions using auxiliary qubits. You see, it was never possible if I have only a single qubit. No matter how many operation I do. Gate operation, that is. Now for variable functions, again, this is my input, this is my output. So in order to take this input to target, I'm using a C0 gate. Okay. If you apply C0, your X will get transferred here. Right? And negation, since it has already been transferred, you just have to apply an extra NOT gate here to get the output as this. Now, the major portion, implementation using an oracle, okay, which is a Deutsch oracle, which is that I have a black box, I'm appending some gates before, some gates after, and I'm measuring the results. Now let's say how this works. Okay, let's say for constant functions, I'm applying my control bit as 0, 0. Here I'm applying X gate, so both are becoming 1 and 1. Then Hadamard, both are becoming 1 by root 2 minus 1 by root 2, 1 by root 2 minus 1 by root 2. Since there is nothing in between, and this is a constant 0 function, after applying Hadamard, going back to unit circle, you will transition back to 0, 1. And here you will transition back to 0, 1. What is this 0, 1? So what is this 0, 1? So when you measure it, you'll get 1, 1 as output. Okay. So for constant 0, if I'm applying 0, 0 as input, I'm getting 1, 1 as output. Let's see for constant 1, and applying 0, 0 as input. Again, the same thing goes, but here I'm flipping the probability amplitude since I have applied X gate. Okay. Flipping the amplitude means instead of going to 0, 1, I'm going back to 0, minus 1. Right? But does this minus 1 change the probability? No, right? Because we are doing a square of minus 1. Right? So again, it will collapse to 1, 1. So in my constant 1 function also, if I provide input as 0, my output will be 1, 1. So both constant functions, my output, if my input is 0, 0, the output I'm getting is 1, 1. Let's see how this behavior goes to a variable function. Now, one of the variable function is identity. Identity is implemented by this operation, C0 operation. So up until here, everything is same. But after applying C0, see, the output of this result at this point, the output was this 1 by 2 minus 1 by 2 minus 1 by 2 and 1 by 2, because I was doing this tensor product of this and this. Okay. If I factored it, I'll get this. So after applying C0, I'll get 1 by root 2, 1 by root 2, 1 by root 2 minus 1 by root 2. Okay. Now this, if I apply Hadamard gate, will transition to 1, 0. And this, if I apply Hadamard gate, will transition to 0, 1. Okay. So while after measuring, this will collapse to 0, this will collapse to 1. Okay. So for identity, my input was 0, 0, and output I am getting is 0, 1. I'm sure it's very daunting to see all this square roots, matrix, vectors, and all those things. But once you get down to it, once you start applying it, once you start solving it, it's very easy. It's basic high school linear algebra. Negation also, what I'm doing, I'm applying x in between, right? So again, here my output will be this at this point. Okay, and I'm going to refactor it to that. Okay, and this again will go to 1, 0 and 0 minus 1. So here in case of negation also, 0, 0 will go to 0, 1. Right? So what this proves, using a single query, my query was 0, 0 only. If I'm getting 1, 1, that means it was a constant function. And if I'm getting 0, 1, that means it was a variable function. So what required two queries to solve in classical system or classical C, the same problem you can solve it using a single query using a quantum system. Right? And in essence, this is a very dummy problem to work upon. But this essentially proves in theory, in some formulations, in some specific application, quantum system are going to be better than classical system. And that is the whole idea behind it. Okay. Now let's go to last section, which is quantum system organization. So this is what an actual quantum computer looks like. And I told you in the beginning, this quantum versus classical is a misnomer. Why this is a misnomer? Because one of the subcomponent of quantum computer is the classical system as well. So a system like a quantum system, at least as of now, cannot function alone. It requires classical system, which is a subsystem or subcomponent of it. And that is why when people talk about quantum computers versus classical computers, in essence, it's actually not true. Quantum computers require classical systems to help them in operations. Okay, so this is one of the subcomponent. The another subcomponent is the control electronics. We shall see what is the role of this control electronics, all those things. Right? I told you, qubits are actually physical entities. And these physical entities are very prone to noise. And in order to reduce noise, you'll have to go to millikelvin level, millikelvin temperatures. For that, you would require a dilution refrigerator like this. Right? And then at the very end, you'll have this like a tip of your thumb chip, which is a quantum chip. Right? But for that chip to work, you would require everything from classical system to control electronics to dilution refrigerator, and most importantly, QPU as well, your quantum processor. This is an actual picture of a quantum computer. Okay. So this monstrosity is what we see here, right? This is that monstrosity. You won't be able to see the quantum chip. It will be like a peck here, and there are so many cables going in and out. This the whole thing behind is my control electronics rack, right? Which again will be connected to some classical system. Okay, and there is a huge amount of wiring that goes on for a simple QPU to work. Now let's look at the operation cycle of a quantum computer. So here somebody has asked how you can use qubit rotation for a problem like scheduling problem. The answer is not that simple. So for any physical domain to get converted into a quantum domain as such, what you would require. So this is my physics. This operations are my classical operations. This yellow one were analog. This is again classical. And this is again goes back to physics. Okay, so you have to have an understanding of physics in order to formulate your equation like that. To give you a very crude example, let's say in primary school we have learned about algebra in general, right? We have seen this uh, problem given in a very English language, that is, let's say Ram and Shyam are brothers. Ram's age is twice the age of Shyam, and all those things. What you do essentially, you write equations for that. So if my Ram's age is X, Shyam's age is Y. So you assign variables, you set up an equation, X plus Y is something, 2X plus Y is something, right? So you set up all these equations and then you solve it, right? The similar thing you will have to do with any physical problem that you want to map with quantum computer as well. So here it was simple algebra. Here you will have to design a Hamiltonian, okay, which comes in physics domain. So you have a very basic understanding of quantum mechanics or quantum formalism in general. Then you can convert this physical problem into a Hamiltonian. So basically, you set up an equation and you design an algorithm for that. What you can do next is then, so the first step was use case identification. Second step was Hamiltonian design. So from use case, you have to design a Hamiltonian. You have to design an algorithm for that. Next, you would come in classical domain. You have to design a circuit for that. So for circuit, typically people using nowadays are using Python as a base language. So I told you Qiskit, Circ, are all these languages you can use for circuit designing. Then you do something called Python to Chasm conversion. So in classical system, you have a assembly code. This is basically quantum assembly code. Quantum assembly, right? So next step was Python to Chasm. Again, we are in classical domain. Next, you have to convert this particular Chasm code into sequence of control pulses. Now, this control pulses are basically analog pulses. So you would define this sort of pulses to manipulate qubits, right? So initialize and manipulate, you need analog signals. So whatever you have seen in that real quantum computer, there are a lot of wires going in and out. So all those wires are not Ethernet cables or any other classical interconnect. They were basically microwave cables and RF cables and all those things, which inputs analog signal to a quantum chip in order to manipulate those things. Okay, so you would generate a control pulse sequence. Using this control pulse sequence, you go back and forth to qubit initialization, then qubit manipulation, and then finally, once you are done with all the circuitry, you will apply a measurement pulse. Measurement again is a pulse. Okay. Once you get the measurement, what you would do is you will apply error correction in again an analog domain. Okay, this is analog error correction. Basically, it has something to do with signal integrity. You will make sure that the output you are getting is actually what you were expecting and so on. Okay. Now you do digitization. You do analog to digital conversion, A to D, and you again go back to your classical domain. The last step is output realization and validation. What is output realization and validation? Classical systems is again domain of computer scientists. We cannot do anything. We have to validate the output, and that will come from theory. So again, the domain is physics at the end. So this is the whole operational cycle of a quantum computer. So whatever experiment you're doing, if you want to implement a real problem, if you want to solve a real problem which is not known, then you have to go through with all these steps. But let's say, for the sake of this lecture, if you just want to get introduced to quantum computer, then what you can do, you can explore algorithms like Shor's and Grover's. They will give you some circuit to work with, and you can solve those circuit using the formulation that I have introduced to you in this lecture. So what I have done is I've just introduced the topic, and you can go back so that you will be able to understand whatever you are reading in future when it comes to quantum. Okay. So this is all. Any questions?
Participants, you can unmute yourself and ask the questions.
Sir, can you just tell us how error correction works for a simple gate?
Right. So what happens is, let's say, just give you an example. Let's say the output of your circuit. So my qubit, initial qubit was this. After some operation, my output is this. Right? Let's say my output was some rotation transformation has happened. My output was supposed to be this, but I am measuring this. This can happen because qubit gets decoherence. So there is something called decoherence. So qubit loses signal integrity, loses integrity over time, right? Because of environmental noises and all those things. And that's why you may get this particular output. So what you can do experimentation again. One method of noise mitigation is noise modeling. So what you'll do, you'll take this as a black box. You put some known inputs and outputs. You have some known input and you have some known output. Your output was supposed to be Y, but you are getting Y dash. So you provide this for multiple inputs. You will get different outputs, and you do the noise modeling first. Once you know that always it's rotating it slightly in this delta direction, you can error correct it, and you can say the actual state was not this, but delta corrected this one. Okay. So one of the very naive way to do this is using the noise model. The same principle applies when we transmit any signal via any communication channel. So you have your communication channel, you are transmitting signal, you are getting some noise. So same principle allows you to work with quantum noise error correction as well. Anything else? I'm sure this all looks very daunting, but trust me, I'll provide this slides if you want. Once you go through with this slides, you'll be able to understand it's very easy. At least understanding and reading portion is very easy. But quantum thinking, going from this to this use case identification to Hamiltonian algorithm is a very difficult step.
Sir, like you said, one of the naive ways is to increase the number of experiments. What do you think? Like, usually we take shots, right?
Yeah.
So, how many shots do you think we should be doing so that thus by naive method the error can be removed?
Okay. So there are two things. Shots, anyways, you'll do for any output measurement. Okay. Because as I told you, the actual state is going to be an arbitrary state. Okay. In order to get measurement, you'll have to do a number of experiments, right? So
Agree,
let's
sir.
say I was supposed to be getting 1 and 0,
Mm.
right? But I am getting 1 minus some delta and some delta here. Okay. Let's say I'm getting this. Then I'm doing it, the experiment, let's say a couple of times, 1 or 2 times. What will happen? I might get 1 as my output, but this is corresponding to 0, right? I
Mm.
might get with a lesser number of experiments, I might get 1, right? So in order for probability to take effect, you have to perform this operations multiple numbers of time. Then again, for known inputs and known outputs, you can perform this experiments for noise mitigation as well. So shots is basically the number of times you are performing your experiment. Now the thing is, here your output has to be deterministic when you are going for noise modeling, right? Otherwise, it's not a point. You won't be able to
Agree.
gauge. But again, there are many ways you can do noise modeling. Why this is important is noise comes from hardware as of now. So quantum computer in itself, we are living in NISQ era, noisy intermediate scale quantum computers. So noisy in itself is there in the abbreviation. What it means essentially is whatever technology that we are adopting, be it superconducting or optical, neutral atoms, whatever underlying technology we are doing is plagued with noise. And they have their noise characteristics, which is given by physics,
Mm.
right? So you can utilize that physics principles, the principles of instrumentation and all those things, and you can apply it for mitigating noise as well. So that
Mm.
is another way to do it. This is very classical way of thinking about it. You perform experiment, you see what my y dash is, what y is what's supposed to be, and you model it. But this is what people are doing practically. So let's say I'm developing a conducting chip. I'll see what type of noise is already present. I'll characterize that chip beforehand, and I would know.
Okay, got you, sir. Thank you for the excellent talk, sir.
Thank you.
Any other questions, participants?
Okay, Sampada ma'am, we can conclude.
Yes, ma'am.
I think there are no more questions.
I will share the screen. It is visible?
Yes,
Yes,
madam.
First and foremost, we extend our heartfelt thanks to Mr. Shashank Sharma sir, whose insight and expertise have illuminated the intricate world of quantum computing. His ability to simplify intricate ideas and shed light on the immense potential of this revolutionary field has greatly enhanced our knowledge and appreciations of its capability and future impact. Sir, please accept our virtual token of appreciations. Thank you, sir.
Thank you,
Please
ma'am.
shoot the light. Yes.
Yes, so thank you for inviting me. It's always good to talk in this topic because, as I told you, I'm learning myself. It helps me understand, it helps me. So, whenever I'm explaining certain things, it helps me